probability factor of 1 to 1. We have normality. I repeat, we have normality. Anything you still can't cope with is therefore your own problem. Welcome to this video on database normalization. My name is Kevin Fiesel. I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. We're taking a little break from Azure Machine Learning here on the channel, though I will get back to it again in the future. For the next few weeks, I'd like to talk about a topic near and dear to my heart, database normalization. This series of videos builds off of a talk that I deliver. This talk is called Perfectly Normal, an advanced primer on normalization. And I will tell you up front, this will get fairly advanced and there will be a bit of formal logic involved because ultimately this is an academic topic. You have been warned. Right, so I do want to call out some great resources up front that have helped me put together my thoughts on the topic. The first one is Database Design and Relational Theory, Normal Forms and All That Jazz, 2nd edition, by C.J. Date. This book is outstanding at digging into the details of normalization, and Date tries to straddle the line between the ivory tower, pointy-headed academic world and the rough workaday world of professional symbol manipulators. My purpose in this series is to take Date's work and push it a little further in the direction of ease of understanding at the loss of some of the academic rigor. The next book I'll call out is Pro SQL Server Relational Database Design and Implementation by Lewis Davidson. Lewis's book was instrumental in helping me get an initial understanding of database normalization, and I can highly recommend his book. I can also recommend the talk he delivered at Data Architecture Day 2020, which the Triangle Area SQL Server Users Group hosted. I'll have a link to that in the description. It's also available on my channel. The final book recommendation I'm going to make here is the Handbook of Relational Database Design by Candace Fleming and Barbara von Halle. My friend Grant Fritchie originally recommended this book as one of the clearest explanations of normalization, and I wholeheartedly concur. Yes, this book is from 1989, so there's a decent chance it's older than you are, dear viewer, but pick up a copy anyway, because it's still a top-tier book. At least until you get to the implementation part, which is intended for late 1980s Oracle and DB2. You have my permission to skip that stuff. Okay, accolades out of the way, let's get down to business. Hello there, welcome to this class on database normalization. If you believe any of the following things, you belong here. First, normalization isn't relevant in the business world. Second, if you have ever used the quotation, normalize until it hurts, denormalize until it works, take a seat. I hate that quotation with the fiery passion of 1,000 suns. Third, if you think that the primary reason that you normalize data is that it minimizes the amount of data you lay out on disk, come on down. Fourth, if your answer to the question of database design is throw more of other people's money at it, you should stick around for a while. Fifth, if you think that getting to third normal form is all you need to know about normalization, we still have some seats up here in the front. And sixth, if you actually think third normal form matters, welcome to class, we'll fix that. Now, because example is the school of mankind, and they will learn it no other, we are going to need an example. Our example is a music studio responsible for managing artists, cutting albums, distributing albums, performing digital marketing, these sorts of things. This particular studio is working on a centralized database system, but the thing is that their application developers don't have much experience. That's why they've brought us in. We're going to teach them how to do things the right way. Let's first define what we mean by normalization. Normalization is a set of logical rules and processes that we follow to improve a database's design. It's important for us to note that normalization works off of the logical data model. From there, we can, at least theoretically, adapt the work we've done on the logical data model to a physical data model for implementation. I think it's fair to ask at this point, why do we need both logical and physical data models? What's the difference, and why not just have one of them? Well, good question, rhetorical me, even though you slipped 3 questions in there. Let's start at the beginning with the impetus behind any database. Some business need. This need might be something like, I need a place to store all the accounting data for this company, or I need to track the status of help desk tickets. We have a need to store data, and hence we need a database. Now we move into the next phase. What does that database look like? That's where we, as data platform professionals, start grilling people and figuring out what it is that we need to store. As we get a better understanding of the domain, we can flesh out what sorts of data elements we need to collect and how those elements fit together. This is the realm of the logical data model. We call it a logical data model because we are not going to bother ourselves with specifics about any database management system. We're also not going to care about how the database performs, how we're going to lay data out on disk, or what mechanisms users will have to query that data later. Instead, we focus on making sure that our data model matches the needs and desires of the customer and that we have as complete a picture as we possibly can get. Once we have that logical data model down, we can convert that into a physical data model. The physical data model is where we start to tie our database design to some particular database management system. For example, we might decide to use SQL Server to implement this database. In that case, we might have to decide whether we want to use in-memory OLTP, table partitioning, indexed views, clustered column store indexes, or any other functionality. We also use the physical data model to lay out things like indexes, file groups, and files. Those things can make a big difference for physical implementation, but they mean nothing to the logical model. And so, for the rest of this series, I'm going to focus on that logical model. The good news is that the advice I'm giving will also apply across any relational database management system. So if you're living in Postgres, SQL Server, Oracle, DB2, whatever, that process of normalization will be the same. Now, because this is an academic discussion, we are going to benefit from using specific terminology to mean certain things. Many database professionals are used to thinking in terms of tables, rows, columns, even cells. Those terms aren't wrong, cells might be, but there are better technical terms which we will use throughout the series, though I will occasionally use the layman's term just to make sure we're on the same page. I'll also tend to use these layman's terms when I'm specifically talking about functionality in a database management system. So I might mention a table in SQL Server or a column in an Oracle table, rather than the academic terms. The first term I want to talk about is a relation. The layman's term we would use here is table, but we lose a bit of nuance because it turns out that we really mean two different things by relation. The first is something that Date calls a relation variable, or relvar. My relational variable is called EMP, and it represents a collection of employees and relevant information about them. At any particular time, the relation variable takes on a specific value, the relation value, which we typically shorten to the term relation. In this diagram, relation variable EMP at time T1 has 3 people in it, Marcy, Jared, and Carly. We collect some information on those people, and we call that the relation value at time T1. Then, at some point in the future, the company hires Yanni to perform legal services. Our relvar is the same, but the relation value has changed between times T1 and T2. By using the separate terms relvar and relation, we can disambiguate the idea of a relation, its relation variable, from the specific details of a relation at a given time, its relation value. That's a hard thing to do when you just use the term table for both of these concepts. By the way, this concept of relations is why we call these databases relational databases. It has nothing to do with joining tables together. It's that the database is made up of relations like these. Also, like Date, I'm going to use the term relation for relation value. That's why the diagram mentions relations instead of relation values. So if I say relation, it means relation value. If I say relvar, it means relation variable. Now, each relation has 2 major components, a heading and a body. The heading consists of a set of attributes, where each is a name and a data type. Employee and department contain character data, and salary is numeric data. The body, meanwhile, consists of a set of tuples. Each tuple must have exactly the same set of attributes as the heading. So for a tuple to fit into rel-var EMP, it needs to consist of values for employee, department, and salary, and those values must fit the appropriate data type for each attribute. Finally, I include concepts of predicates and propositions below. We won't dig into these very much during the series, but the idea is that we can describe any tuple of rel-var EMP using our predicate. Meanwhile, a proposition is a true or false statement concerning a tuple inside of a rel-var. That's the short version of terminology, and don't worry, I will reiterate some of this terminology as we go along in this series, as that's the best way for it to make sense. Now let's talk about the real goals of normalization. There are 4 goals I want to lay out for us as we perform normalization. The first is to remove redundant data. Now, some of you may be jumping up at your desks, ready to scan back earlier at this video so you can quote me as a gotcha. But let's go to the instant replay. Third, if you think that the primary reason that you normalize data is that it minimizes the amount of data you lay out on disk, come on down. Removing redundant data is a reason, but it is not the primary reason. A more important reason is this second one, fixing incorrect designs. Normalization helps us make certain guarantees about data quality, and that is, especially in an era where I can buy a 10 terabyte hard drive from Amazon for less than $200 US, this is a much more significant benefit. This leads us to our most important reason of all. Normalization helps us achieve a design which is a good representation of the real world. At the end of the day, our databases are relevant inasmuch as they reflect the business processes which led to their creation. If our database does not reflect reality, people will struggle to use it and will eventually abandon it altogether. Normalization provides us certain ways of thinking which we can apply to design, which will later help us ask certain questions of our subject matter experts and get to a better design. The final goal we have for normalization is to simplify the statement and enforcement of certain integrity constraints. Things like primary keys, unique keys, foreign keys, that sort of thing. These are our goals. But before we wrap things up, I want to talk a bit about normal forms. Anyone who's been around in the database world for a little bit has heard of some normal forms. First normal form, second normal form, third normal form. Some of you probably know about a fourth or a fifth normal form, but it turns out there are more. Oh, so many more. Remember, normalization is an academic exercise, and when you let academicians loose, they start categorizing things like Aristotle on a 3-day cocaine bender. Frankly, the 11 entries on here aren't a complete list either, but it turns out this is okay for us. By the way, if you're curious about that fifth normal form block, there's some fuzziness and debate about whether fifth normal form and project join normal form are exactly the same, or if there's a minor difference between the two. But we are now going to hand wave that difference away and never speak of it again. Because here is what matters. The official Catallaxy Services tier maker listing of normal forms ranked by importance. In the S tier, we have Boyce Cod normal form and fifth normal form. These are the elites, and we will have entire videos dedicated to each of them. The A tier consists of sixth normal form, which is a really powerful normal form, but not always necessary. The B tier contains first and fourth normal forms. We will have videos on these two as well, but I think both normal forms are overrated. Below them, we have the C tier. The C tier is my default dumping ground for what I consider overly academic normal forms. Basically, each of these normal forms is relevant in very specific circumstances, but the likelihood that you will ever find a use for any of them in the wild approaches zero. For that reason, we will go back to ignoring those normal forms. And at the very bottom of this list, we have second and third normal forms. Yes, that's where they belong. And if you want to learn why each of these normal forms belongs in the dumpster, stick around, I'll explain myself. But for now, class dismissed. That's going to do it for this video on database normalization. Stay tuned for the next video in which we get started at the ground floor with first normal form. We'll have links and show notes in the description below. And until we see each other in the next video, take care.